ocean is considered as the cradle of life, where life originated 3.5 million years ago and formed a huge treasure house of life and resources. India, with its long coastline and large exclusive economic zone (EEZ), recognized the need for technology development for ocean exploration and for harnessing resources in an environmentally sustainable manner. The National Institute of Ocean Technology (NIOT), the only civilian ocean technology institute, was started when this need was recognized by the then Department of Ocean Development (DoD) and now the Ministry of Earth Sciences, Government of India in 1993. Subsequently, as the activity started growing, a separate campus at Pallikaranai, Chennai was established in the year 2000 with a mandate to design, develop and demonstrate technologies for the oceans. Some of the major non-living resources that the oceans offer are polymetallic nodules, cobalt-rich manganese crust, hydrothermal deposits and gas hydrates. As a pioneer investor, India was allotted 75,000 square kilometer area in the Central Indian Ocean Basin (CIOB) by the International Seabed Authority (ISA) United Nations for the survey and exploration mining of polymetallic nodules at 6,000 meters water depth. Surveys estimate the resource potential of polymetallic nodules in the area as 380 million tons, containing 4.7 million tons of nickel, 4.29 million tons of copper, 0.55 million tons of cobalt, and 92.59 million tons of manganese. Developing suitable technologies for safe, sustained and eco-friendly exploitation of these potential resources is also of strategic importance. Mining of manganese nodules from the soft ocean floor at a depth of 5,000 to 6,000 meters is a major technological challenge. In India, the design and development of the deep-sea mining system has been taken up by NIOT under the aegis of Ministry of Earth Sciences. To minimize developmental costs and associated risks, initial efforts were focused on realization and qualification of machinery for long-term operations at shallow waters, and a flexible riser concept with a crawler-based mining machine was chosen for the development. Development of this complex technology is being attempted in a phase-wise manner. In the first phase, an underwater mining system was developed and tested for mining seafloor material for a short duration at 410-meter depth. The subsystems such as crawler-based mining machine, flexible riser system, positive displacement pump, electrical systems, sensors and control systems proved during the development phase. The mining system was tested for long-term operation for pumping seafloor material at 452 to 515 meter depth. The machine was modified for augmenting with a mechanical collector, underwater crusher for testing at shallow waters with artificial nodules. Artificial nodules were prepared with mechanical properties close to that of manganese nodules. After the long endurance tests, a remotely operated subsea artificial nodule laying system was developed for creating a small mine site similar to that of the one in the CIOB. The system was tested successfully off Chennai coast. The augmentation of the deep-sea crawler with collector crusher for deep ocean mining of polymetallic was done as the next step. The system was tested in the sea by pumping artificial nodules laid on the seabed. Efforts are on to develop crawler-based mining machine for 6,000-meter depth. The main challenge is to develop the seabed crawler that can move on the soft seabed and flexible riser for pumping the nodules to the surface ship. Buoyed by the successful demonstration of the system at 890 meters water depth, NIOT scientists are gearing up for 5,500 meter operation. The knowledge of bearing and shear strength parameters of the soil are required for designing the integrated mining system for 6,000 meter depth. The shear strength of the soil also provides useful information for the maneuverability and control of the mining machine. It is also imperative that the mining area be delineated to eliminate vulnerable areas of low strength where the equipment may sink suddenly beyond recovery due to anchoring of the machine. A remotely operable in-situ soil tester has been developed for 6,000 meter operations. Soil property measurements and equipment's performance at 5,462 meter water depth in the central Indian Ocean basin has been successfully carried out. This was also the first time that the polymetallic nodules present on the seabed at CIOB were actually seen remotely and photographed with high clarity by an Indian system. Incidentally, this was the deepest point reached by Indian-made equipment and successfully recovered. As a part of the Indian Deep Sea Technological Development Program, NIOT developed a 6,000 meter depth-rated deep water remotely operated vehicle ROV named ROSUB 6000. The ROV is an unmanned electrical work class underwater vehicle and has 7 electric thrusters for maneuvering in all 6 degrees of freedom in the manual or automatic mode. The storage winch on the mothership houses the electro-optic umbilical, and its operations are with the launching and retrieval system LARS and other deck gear, which launches the ROV and tether management system TMS below the splash zone in the docked condition. After reaching the desired depth, the ROV is undocked from the TMS for desired operation in deep waters. The system was utilized for gas hydrates exploration in the Krishna-Godavari basin in the Bay of Bengal at about 1,000 meter depth. Polymetallic manganese nodules in the central Indian Ocean basin at 5,289 meters. And hydrothermal sulfides at the central Indian Ridge in the southern Indian Ocean near the Rodriguez Triple Junction at 2,800 meter depth. ROSUB 6000 was deployed for the IAF aircraft AN-32 search operation in Bay of Bengal at a depth of 3,400 meters, and targets were verified at the 3 given locations. Based on the experiences gained in the design, development and operation of ROSUB 6000, an ROV useful for polar and shallow water regions rated for 500 meter water depth was developed. The vehicle PROV is qualified for its performance in NIOT Acoustic Test Facility ATF and for the low temperature conditions in the environmental chamber. The vehicle could be launched from any vessel of convenience. Doppler velocity log and compass module are used for underwater position estimation. The vehicle is equipped with adequate cameras and lights for visual imaging, sector scanning sonar for acoustic imaging purposes, and an oceanographic sensor suite comprising of dissolved oxygen, conductivity, irradiance sensors for water column observation. After its qualification at Idukki Reservoir in Kerala, the PROV was utilized during the 34th Indian Scientific Expedition to Antarctica during January-April 2015. The vehicle was deployed in the Priyadarshini Lake near the Indian base station Maitri, where the lake bed images are taken. Subsequently, the vehicle was deployed in the new Indian Barrier Ice Shelf region up to 62-meter water depth, where the ice sheaf images were captured using the sonar. PROV was used for coral reef expedition in the Andaman and Nicobar Islands of India, which are the hotspots of biodiversity with their unique coral reef bioreserve. High-definition coral reef images were captured up to a depth of 30 meters near Andaman Sea, North Bay and Chidiatopu and Bay of Bengal Islands, forming a part of Mahatma Gandhi Marine National Park of Andaman. Globally, laboratory and field investigations are in progress for non-conventional energy resources. Coalbed methane, shale gas, and gas hydrates are some of the potential alternative sources of energy. Gas hydrates are crystalline substances composed of water and hydrocarbon gas molecules in which solid lattices of water molecules trap gas molecules in a cage-like structure known as clathrates. Estimates show that the methane stored in the form of gas hydrates is in the order of approximately 950 trillion cubic meters within the Indian Exclusive Economic Zone. NIOT is involved in technology development for methane hydrate research in India. Scientific exploration for gas hydrate was conducted with the help of NIOT ROV. ROV interfaced with scientific payloads, made dives at a depth of 1,037 meters and 1,019 meters in Krishna Godavari Basin in Bay of Bengal at sites identified by NIO and NGRI Hyderabad. The ROV-based multi-beam sonar survey was carried out within 80 meters square from an altitude of 25 to 30 meters above the seafloor at a depth of 1,019 meters. Seafloor sediments were collected with short push corer and water sample was collected using the manipulator. The observed mound-like features are similar to the chaotic submarine seafloor, disruption craters and pingo-like structure observed elsewhere at gas seepage margins in the deep ocean. The observed spiral whip coral colony was similar to Kiribati spiral's indicator of chemosynthetic habitats and methane seeps. To cater to the need for exploration and ground truth validation of gas hydrate occurrences in Indian waters, and to quantify the resource in the Indian continental regions, NIOT has developed an underwater wireline autonomous coring system ACS. System is capable of obtaining 100-meter core up to depth of 3,000 meters. ACS uses wireline drilling technology. A proper characterization of hydrate-bearing sediments requires coring, recovery, and testing under pressure and temperature within the stability conditions. For this point of view, ACS has a pressure core sampler with a length of 1.5 meters in 36 mm diameter. This tool can be used for sampling the gas hydrate at in-situ pressure. The ACS system comprises subsea coring, drilling unit, launching and recovery using A-frame and deep-sea winch, control console, deck powerhouse, control software, umbilical cable with termination assembly. The ACS is fully controlled from a surface station based on the sensor feedbacks. Sensors and camera images provide information on drill functions. These sensor data are used as the input for the ACS real-time control software, which generates the necessary signals to perform the intended tasks. This has been depth qualified for 3,000-meter operations and drilled up to 40 meter below the seafloor at 850-meter water depth off Chennai. System was landed at soft seafloor of KG Basin gas hydrate site with soft foot assembly. Further trials and coring at KG Basin gas hydrate site are on the anvil. To understand the feasibility of methane hydrate extraction from gas hydrates, studies are carried out at NIOT by numerical simulations, laboratory experiments, and using gas hydrate reservoir modeling packages. Electrothermal heating and depressurization techniques were applied to the field data sets of Krishna-Godavari Basin, Mahanadi Basin, and Andaman reservoirs. Studies on subsidence and environmental impact due to hydrate dissociation are in progress to develop the EOI for developing the production methodology. The underwater remotely operated vehicles and autonomous vehicles have their own advantages and limitations. A manned research submersible can combine these advantages. Hence, NIOT is in the process of developing a manned submersible with a depth rating of 6,000 meters to aid direct human intervention. This manned submersible with 2 scientists and a pilot on board with suitable observation, sampling and intervention tools can be an aid for deep ocean exploration and intervention. Vehicle will have a 12-hour endurance with an emergency support for 72 hours. The development of the Indian human deep ocean submersible Matsya 6000 is in progress, and the Indian Samudrayan will make its deep ocean voyage soon. The statement that about 70% of the earth is covered with water is not a mere cliché. It means that 70% of the earth resources are still unexplored and are available to mankind. Development of reliable technologies for the exploration and harvesting of these resources is the need of the hour. With ever-evolving mandate of the National Institute of Ocean Technology and the Ministry of Earth Sciences, Deep Sea Technology Group continue their inner space odyssey in the development of these technologies.